Okay, welcome back to the third part of the video tutorial for the 2008 mechanics paper. This is still on question 2. So, rower goes across to the pole swing. The swing hangs on a rope attached to a uniform beam, as shown in the diagram. The beam is 3 meters long and has a mass of 35 kilograms. The angle between the steel wire and the beam is 37 degrees. The tension force in the steel wire is 1500 newtons. So that's this steel wire here, 1500 newtons. And so the rope is different to the steel wire. Although it looks kind of like this is going through a winch and this is all one thing, this steel wire is actually not the rope, they're separate. Okay, what's the question? The force exerted on the beam by the steel wire can be split into two components, which makes sense because it's on an angle, so it's got a downwards, or however you look at it, a vertical component, and then there's the horizontal component, so that makes sense. Show that the vertical component of the force exerted on the beam by the steel wire is 900 newtons. Okay, so I'll just draw another triangle here, a bigger one, because essentially we only need the area with the force, with the steel wire and the beam. So we've got 37 degrees, 1500 newtons, and we need to find the vertical component, and instead of just saying that this is part of the pole, we can say that this is the vertical component of the tension, and we can just use easy SOHCAHTOA trig here. So that's going to be O, that's H, so the opposite, the hypotenuse and the adjacent. Oops. So these are our three choices. We have the hypotenuse and the angle for the adjacent, and we need to find the opposite, so we're using this here. So that means that, write it out like this. Sine 37 is equal to, times 1500 is equal to O. So that's 902 newtons. Don't really need to put anything, but we basically, although it's not exactly 900, we've used exactly what they've given us, and we've proven that it's approximately 900. So if you're using 1 SF rounding, which they appear to be using, then you can say that that's correct. And it has proved it. It's more or less that tension force in the steel wire might be slightly different, and realistically that's more or less proven it. Well, it has proven it. By calculating the torques on the beam about the pivot, calculate the tension force in the rope. Okay, so looking back at the formula sheet, torque equals force times distance here. T equals Fd. So we know that the beam here, we underlined it here, is 35 kilograms, which is important because we need to work out the essentially the forces acting on the beam. So this is going to be equal to 35 times 9.8, the force of gravity, to convert the kilograms into newtons. So that's 343 newtons. And that's a bit confusing here. So they've got the tension in the rope. The 900 newtons here isn't actually the tension in the rope. This is the vertical component of the tension in the steel wire, which we've calculated. So that's a little confusing. I don't know if you could see that before. So yeah, we don't have the tension in the rope yet. This is what we need to work out the force acting here, because we're finding the torque about the pivot, but we don't actually have the tension. that's just a little ambiguous. So the torque is equal to the force times the distance. So this is a 3 meter beam, and obviously the weight of the beam is always felt in the middle. So this is going to be 1.5 times 343 plus the force. Okay, so this is the downwards force here, or the downwards force, and this is the vertical component, the tension in the steel wire, which is going upwards. So we need to prove that 900 times 3 is equal to this times the tension in the rope. So that's times 3. Basically we've got 900 upwards, so that 900 times 3, which is... So that's 2700 newtons, is going to be equal to downwards 2700. So that means, just putting that in here, 1.5 times 343 0.5 plus 3 ft. So we can move this around a bit to make force times tension, or the force of tension, the subject of the equation. So we get 2700 minus 514.5 is equal to 3 ft. So that means that ft is equal to all of this divided by 3, which is equal to so I'll leave that there. 728.5 newtons. So that makes sense because we've got the force here pulling down and the force here pulling down, tension in the rope and the tension in the steel beam here, and obviously these two don't add up to 900, but when you compare the distances and the torque, then obviously we know that it does, and that makes logical sense when you look at the numbers, so that's probably right. Rua then climbs onto a trolley and Tahi tows him with a rope. As shown in the diagram, Rua's mass is 65 kilograms, and the mass of the trolley is 11 kilograms. The tension force in the rope attached to the trolley is 95 newtons, and the rope is at an angle of 45 degrees to the ground. Okay, there is 35 newtons of friction force on the trolley. Calculate the size of the trolley's acceleration. Right, so they've given us lots of forces, masses, so acceleration shouldn't be too hard to find. Just like with the last question here, we had to find the vertical components. We're looking for the horizontal component here because the rope is pulling with a force of 95 newtons, but it's on an angle, so we need to find what the horizontal component is. So, making another triangle, I'll do it over here. Okay, 45 degrees. 95, and we need to find, probably shouldn't put that. We need to find the adjacent here. We don't need to find the opposite. So this is the hypotenuse and the adjacent, so if we go back to these, obviously we'll be using this one. We've got the hypotenuse and we have an angle, and we need to find the adjacent. So cos 45 times 95 is equal to 45 times 95. Okay, so the horizontal component is 67.8 we can round that to 67.2 newtons. And it probably isn't going to be important what you choose to round to, because it's probably going to, we'll have to give it to the original number of significant figures anyway. Although generally I would like to round it to 4 dp, but so that's what the actual horizontal force is. So this is 67.2. So we need to find the acceleration. F is equal to ma. We need to find acceleration, so F over m is equal to a. We have the force, which is 67.2 divided by the mass, which is 65. Oh, it's 65 plus 11, so that should be 76. Yep. Divided by the mass, which is equal to so that's about 0.88. We can say that's 0.9 ms. -2. Is that right? Oh, wait. I've done something. Oh, yes, that's right. We've got the... I thought that... Yeah, that didn't seem right. The 35 newtons of the friction force here, we forgot about that. So this is actually going to be 67.2 minus 35. Thought I'd forgotten something. 67.2 minus 35. Yeah, that's very different. Divided by 76 is equal to 0.4. Or 0.42, I suppose. Yep. And that's not a whole lot of acceleration, but when you consider how heavy he is, and it's someone pulling him, so it's not going to be accelerating at like 10 meters a second, because it's probably got a very, very small velocity anyway when it's just someone pulling on a rope. The rope stretches 1 centimeter with 95 newtons of tension force. Calculate the elastic potential energy stored in this stretched rope. So this is going to be involving Hooke's law, I believe. Okay, so the force in the stretch rope, yep. So F equals minus kx. And x is the distance here, k is the spring constant, and force is the force that's stored. And essentially what we can do is, we don't know what the spring constant is, but we know what the distance is, and we know what the force is. So this is equal to x is going to be equal to 0.0, that's 10 centimeters, 1 meters, and the force is equal to 95 newtons. So that means, where is it? If we divide both sides by the distance, then we'll get... Is that negative k? That doesn't make a whole lot of sense. I think for this circumstance it's just going to be positive k is equal to what is it? Force 95 divided by 0.01, which is equal to, it's not very clear. So that's timesing by 100, which is going to be newtons. So that's the spring constant, and if we go back to the formula sheet here, Then we've got, where is it? Doesn't seem to be here, but the energy you can find, or maybe I'm just missing it, but it's basically exactly the same as the kinetic energy formula, but what you have is the potential energy. You've got E is equal to half of K times x squared, so it's the same kind of format as kinetic energy. It's obviously very different though. So this is going to be equal to half of 9500 times 0.01. Oops, that's squared. So 9500 times 0.5, which is obviously half times 0.01 squared. So that's equal to 0.475 joules. You can round that, but I'll just leave that at that, I suppose. That's an annoying number to round. It's not a nice one, like 0.41 or something. Okay, after a while, Ro is rolling at a constant speed. He throws a ball vertically upwards relative to the trolley, so he's still in the same trolley. There's a ball in there, apparently, somehow. How does he fit in there? That's strange. I suppose he can. Okay, after a while, he's moving at a constant speed, so that's important. He throws the ball vertically upwards relative to the trolley. Again, air resistance is negligible. That's almost always the case. Where will the ball land? Okay, explain your answer. You may draw a diagram in the box below. So let's do that first. So we've got the trolley. And we've got Ro inside. His arm's going down. So he's throwing a ball up, and if it was stationary, basically what would be happening is the ball's going up, and then it's just going to come straight back down again, and it's going to end up in the same place. But that's not exactly the case, because the car, or the trolley rather, is moving. So that means when the ball goes up, when he throws the ball is going to be moving in relation to the trolley rather than just straight up in the air. So there's actually going to be a force pushing the ball. Instead of going straight upwards, it's going to travel on a curve because of the horizontal direction of the trolley. So essentially what's going to happen is the ball is going to travel like this, and it's still going to end up in the same place relative to the trolley, but it's going to travel in a perfect parabola because air resistance is negligible, and it's just going to follow all the regular I don't think air resistance would even change it. It's just going to follow all the regular rules for projectile motion. So the ball goes up. It's probably going to go a bit higher than that, but... and it's going to end up in the same place relative to Ro. My diagrams are terrible. But what's important is that because the trolley is moving, the ball is going to be moving in a curved path rather than straight up. Because even though it is vertical, it's vertical relative to the trolley, so that's the important part. Okay, so the ball... and it makes sense that it'll land in the same spot because it is being thrown vertically upwards. So it should, in relation to the trolley, it will land in the same place on the trolley. It's just that the trolley will have moved in that during the time. So the ball will land in the same place relative to the trolley. This will be some distance. We probably could work out the distance somehow, but that's not important at all. Some distance away from where it was thrown. This is because the ball, or how should we say this? The ball has a horizontal speed, and unchanging. And the reason it's unchanging is because there are no forces slowing it down, there's no friction or anything. And with projectile motion, it's just really the vertical velocity that's changing. That's the only reason it really comes down. Oh, I don't know if the camera was in the right spot, if you could see my diagrams before. So the horizontal velocity is going to be always the same, basically. And the trolley's not slowing down, and not that that really matters, but when the ball was thrown at that speed, that's the speed it was moving at. Yeah. However, so it will have travelled. Is there room? I'll write it down here, I suppose, or I'll skip to here. So it will have travelled a distance, I suppose. A distance relative to the ground. You probably don't need to add all this on, but I think it's important. Travel a distance relative. But relative to the trolley. It will. That looks like land in the same place, provided the trolley doesn't slow down. Also constant. Oh, I don't know if you can see that. Okay, Ruth throws the ball vertically at 9.8 meters per second. Calculate how long it will take for the ball to return to the same place. So this is going to be back to kinematic equations again. Like the first question, they start and end on a kinematic, which is funny. Well, so we've got we don't really have the distance, so this one here isn't going to work. We have the time, kind of, because we want to find how long it takes, so we're going to be using the time. So this one here isn't going to be very useful. We could use this one here, but we have the acceleration of, well, the acceleration of gravity, which is going to be pulling the ball downwards. So this one here isn't going to work because we don't have that. We only have distance again, which we don't have, and velocity. And I'm going to be using this one because we have the with projectile motion. I talked about this before. I think the final velocity and the initial velocity is the same, and the acceleration is obviously going to be gravity. So they made it nice and easy as well, because Rua throws the ball vertically at exactly 9.8 meters per second. So what we have here is Vf is equal to Vi plus At, and the velocities are vectors, so essentially what we have here, the final velocity is when the ball is coming back down. So the velocity is going to be negative, effectively, because it's the opposite direction of where it was thrown. So we're going to have negative 9.8 is equal to 9.8 minus, and again the acceleration is also 9.8 time, which is equal to, well, we can take this over here and divide by -1, so that's just going to give us 2 times 9.8, or rather negative 9.8 minus 9.8, which, yeah, negative, I'll just do this step by step anyway, is equal to negative 9.8 t, so we can just divide by -1, so 19.6 is equal to 9.8 t. So we get here t is equal to 19.6 divided by 9.8, which obviously 19.6 is just 2 times 9.8, so this is just going to be equal to 2, and that's 2 seconds. Oops. Right, and I think that's it. Yep. And I think there was one question earlier on in part 2. Where is it? Here. Okay. This collision is in elastic state, what this means. So that's going to be, so if it was elastic, that would mean that kinetic energy is conserved. But it's not elastic, so that means kinetic energy will not be conserved with the collision. I got confused with velocity and stuff before, but because I saw collision and just thought momentum straight away. Okay, kinetic energy will not be conserved. And that's it. I hope that was somewhat useful. See you next time.